Yeah, so these are the topics, and we already started variational autoencoder last time, um, and we did up to KL between two Gaussians. So we will quickly look at the objective. So if you recall variational autoencoder, then we have the encoder and we had the decoder. Okay, so this q phi z given x is the encoder. So it takes an x and then it learns to encode a vector z, and then the decoder tries to get back the x. So this will be p theta x given z. So it takes given z, it tries to produce x. So this is parameterized by theta. This is the neural network. Okay, so this is neural network and this is neural network, and this is parameterized by phi. So this is where we were. So these are the notations, and what we want the encoder to do, which is q phi z given x, is that it should become a normal distribution with mean mu theta and variance sigma phi, and obviously these are produced by the neural network. So as we have seen in the last class, so to produce this distribution, this is characterized by two parameters, mean and variance. So basically it is supposed to produce a vector like this, and these are multidimensional, okay, because single dimensional won't work. Okay, in a high dimensional problems, your latent vector should also correspond to higher dimensional problem. Latent vector should also correspond to some high dimensional, not higher, like high dimensional distribution. Okay, so this is a vector of mu. Okay, it cannot be just one. Okay, that will not be expressive. And this is sigma phi. This is vector of variance, obviously. So basically this neural network produces this vector. That's it. Okay, now it is your job to pass this to a sampling function, which could be your Python code, and you can say that, okay, these are my mu theta, these are my variance sigma phi and mu phi, and generate a sample for me, and that will generate a sample z, and then you will take a z from there, and you will ask the decoder to now learn to get the real vector x. Okay, so this is the process. As such, the process is quite simple. So algorithm is quite simple. Okay, and it's literally what I said is you can just code immediately. Okay, so you let neural network, now even the choice of neural network, there is no real restriction. Okay, you can choose neural network that you want, but since we will be working with images, then you better use some CNN type architecture here. Okay, so it will be usually CNN, and decoder could also be CNN, although we will see there are many ways to kind of play around with this. So that's more or less the variational autoencoder. Okay, it's very simple, maybe 7-8 lines of code. That's it. You have encoder module, you have decoder module, and so on. It's just that we wanted to go through the maths part as well. Okay, so that's it, right? So this nn phi is what we are calling this guy, nn phi, which is yeah. So this is q phi. So this is the context. This is what we saw in the last class. In fact, we did more than that, but just to recall these notations. So obviously we are also looking specifically of this type, where the variance is like a diagonal. Okay, so to keep things simpler. So then we also saw this that variational autoencoder. So when we deal with these things, the supervised learning, obviously the main thing that we end up with is some kind of a loss, right? So how do you define a loss function? Okay, so basically overall you want to supervise, so basically it should be like optimization of these parameters, right? So then loss function is a critical part there. And this loss function is what this loss function comes from the maths, obviously, because what is a good way to define a loss? That itself. So we saw that this is some variational lower bound. It's derived from variational lower bound. So this is something we derived in the last class using those VLB bound, variational lower bound, and that's it. So if we have to understand this loss, then this is the KL divergence of Q phi Z given X, okay, and then the PZ, and we have the log likelihood for the decoder, okay. So this turns out to be basically a reconstruction loss, because P theta, if you see this as a normal distribution, and there is a way that we can work this out. Right now I will not try to do that. So it will turn out to be something like this. X, so X hat is your reconstructed, X was your input, so actually it derives like that, okay. I'm skipping the derivation of this part specifically. So you can call this as reconstruction error. And this is happening because if you work out the expressions P theta, also you are assuming, let's say, some normal distribution, then log of exponential of X minus mu expectation of X minus mu of or like X minus X hat. That's how it comes up in the numerator. So we can do that if it's yeah. So that's why this will be called reconstruction error, and this is somehow doing the fixing the matching, that whatever the whatever distribution the encoder is trying to generate, that should match the one that is being used to kind of it should match the target, let's say target. So let us go back to the diagram here. Yeah. So what is the target, right? So here it will produce some, of course I force it to be a normal distribution, that's right, but it could become any arbitrary normal distribution, like so, and why should I care? The point is, if it produces some bunch of first half is some means, and the second half of the vector I see them as a variance, then so what, right? I mean, it generated something random, and I treat them as means and variance, and then I will sample from them, and I will try to kind of regenerate the image. Well, for the generator, which is the decoder, okay, for decoder we want some simple distribution that will be push forwarded to, and we all know simple distribution would be something like standard normal, so something like this. So rather than keeping this guy a arbitrary normal distribution, we can do this step where we say, well, I want you to be actually standard normal. You start behaving like a standard normal. So basically we are training this decoder network or the encoder network to produce normal distributions, but close to like standard normal, and this will also help us later, okay. Because there is something called reparameterization trick, and that we can do and keep things kind of separate. So if we go back to the loss, then this, as I said, is a reconstruction loss, and this is the KL divergence between the distribution produced by the encoder and what we want it to be, okay. So in this case, let's say we want it to be standard normal. So we could have replaced this by 0 and identity matrix, okay. So this will remain our this will be our VAE objective. Now, according to our assumptions, these are this is some mu and phi. So basically we need to compare KL with KL for mean mu and then standard normal, right? So this is like the normal distribution, and this is the standard normal distribution. So, but for this, we did that in the last class, that k-divergence for two normal distributions PQ can be explicitly computed. Can be explicitly I mean in closed form expression. Okay. So we did that derivation in the last class. So we are not really worried about this term now, okay, because this we have a complete hold on that. We explicitly know that expression. Okay. So obviously when we do optimization for this, we have to take gradients, right? So now we are worried for the gradients. How, and to compute the gradients, we want to know what these guys are really. Okay. So the second part seems okay. There is explicit calculation there. We are a bit worried about the first part. So first part, we have to do some form of estimation or Monte Carlo estimation. So when we see expectation terms, then we get a bit of relief that once expectation is there, it tells me that if you have a good enough sample, you can estimate. So if I have expressions, however complicated, but in the expressions I see expectations, then from computation point of view, I'm kind of still okay in the sense that I will always say, let's go for Monte Carlo estimates. But Monte Carlo estimates exactly means that you will approximate via samples. Okay. So if you have this, then that's what we may do. So in this case, what we are saying is that it is not easy to get some closed form expression like you had in the second term. Although k-divergence also involves expectation and so on, but in this case, yeah, you have to explicitly look at some. So this is something we did in the last class. K-divergence between two normal distribution and let's say standard normal distribution. So this came out to be explicitly this. So which is nice. So we did this derivation in the last class, so we will skip that. And yeah, so we had this derivation. Now, so coming back to the loss, this is the loss, and we are done with this guy because yeah, we have the expression. So basically, so L, this loss is still intractable since the expectation computation with the E Q phi, if you really think in terms of exact expectation, then it requires evaluating neural network transformations for all possible Z. So that will be a bit tricky if we have to do it for all possible Z. So obviously we will approximate. So Monte Carlo helps replace expectation with Monte Carlo. So by Monte Carlo, as I said, you replace explicit computations via some sample. So in this case, you sample some Z. Okay, not necessarily all possible Z. So you are not really precise, but you are expecting a Z which is a good representative, and then you take a you say that the expectation is similar to kind of having approximated this by log p theta x given Z. So Z is like one of the sample, but again this is one possibility. Okay, like the way it is written, as I also said in the last class, expectation is all about average, so it doesn't matter, and no one stops you from sampling lot more. So I would suggest that you go for more of these. Okay, so 1 by k log p theta x given zi and I. So basically you do this average on lot more so that your expectation approximation is better rather than doing just one. Of course, you have to look into computation trade-off, like how complex these how much time it takes to do this. This number of samples, obviously you are getting better and better to this expectation, because sample mean is an unbiased estimator of the true mean that we know. So this is sample mean. So as sample mean sample sizes grow, obviously it is approaching the true mean. So this is what they're saying is that the first term and the expectation that needs to be computed the first term, as such we cannot have a closed form, but you may always approximate like this. So that's what we are going to do. Now with this approximation, obviously we can go ahead and do the gradient calculations. So we were supposed to do gradient calculations of this guy. But then now if we look at the gradient with respect to theta, then we have this. This is approximated just by this guy. So if I look only as theta, then it seems like there is no theta dependence here. So that's why it seems like I'm ignoring this completely. So if I have to take gradient with respect to theta of this guy, then only the first part of the term is needed, and within that, after Monte Carlo estimation, we get this, and hence if I have to do now grad theta, then I just do grad theta of this guy, so which is grad theta log p theta x u and z, right? So this is how we get gradient with respect to theta of L. So we needed two gradient because there are two parameters in the loss. Grad theta, so grad theta it seems we have, and we have grad phi. So grad phi also we have in the second term there. Okay. So and yeah, so grad phi is we have here. Yeah, also in the first term actually. Yeah, so grad phi is also there in the first term. So this is our grad theta, and now we are looking at like it remains to compute the gradient of the objective with respect to grad phi. So again, I won't be worried about this, as I said, because this was explicit form. So again, you are looking at this guy, whether grad phi we can do, but obviously you can do it on samples. So basically, again, Monte Carlo estimate will be useful when I have to do grad phi for the first term. Grad theta for the first term we dealt with via this, but again grad phi is also involved in the first term. So there is still this thing remaining. So when you look at the grad phi, there is a bit of a concern here with the grad phi, because if you look here, your loss is sitting somewhere here. Okay. So grad phi tells you grad phi is for the encoder. So grad phi, what it suggests is you are supposed to go in this way, right? And all this is happening via and there is an intermediary here, which is z, and z you get x hat, which is reconstructed, and this is your input x. Okay. So there is a little bit of a concern here. If you see, when you have to flow the gradient through this route, if you have to flow the gradient only for theta, then there is no such problem, in the sense that until here things are kind of deterministic, in the sense that once you sample z, that z is there. I mean, once you take the z, it's fine, right? But when you pass through this, right, you are passing through a gate of kind of randomness. So the z that you sample through, and you're supposed to flow the gradient through this z, but the sampling process itself is from some random some distribution, right? So how will you take derivative through this? Okay. So there is this additional concern here while we go through the gradient for phi. Okay. So the idea is simple, that z is seen as a sample taken from normal, and well, we are expecting this to be close to standard normal, but initially it won't be, obviously. So initially it will always be behaving like this, with some mu phi which is not necessarily 0, and sigma, sorry, and so sigma which is not necessarily identity. So but if you sample z from here, then you somehow lose track of these mu phi and sigma phi also. Like so technically, how will you pass the gradients, right, through z? Okay. So or overall, let us keep it simple. How do you compute this? Okay. So there are a couple of things we will see what to do in this case. Obviously, if I could explicitly make them kind of expose the mu phi and sigma phi explicitly, and kind of keep the randomness separate somehow, that might help to doing the gradient flow. So that will be the role of reparameterization trick. So overall, what reparameterization trick says is this: computing this gradient is not easy, and let us see. So there is a argument behind that. So obviously we will go for Monte Carlo estimation of this guy, okay, and this will be held by the reparameterization trick. So this is the trick which doesn't really look much like a trick if you are into distributions, because I know that Z is sampled from a normal with mean mu and variance sigma phi. So I know very well, if I know some properties of the normal, that normal distribution can always be generated. So this sample Z that I just sampled could also have been generated via. So this could have been done in two steps. First, I generate from standard normal some epsilon sample, and then if I scale it by sigma phi, and if I translate this by mu phi, then it is an easy exercise to check. These are easy things. I mean, usually exercises. So this will indeed be normal distribution with mu phi and variance this. But for our purpose, it was essential that we fall back on the standard normal distribution. Okay. First of all, it is exposing this mu phi and sigma phi. That's one thing during gradient flow. But another thing is that we fall back on the standard normal, which has some justification as well. So, but for the moment, let us look at just this trick as a method, and we will justify this in the second slide. So overall, what is going on? We were sampling Z from normal distribution with mean mu sigma phi, but what we are saying is that no, you do it in two steps now. You first sample from standard normal, and then you see Z as this. Okay. All right, and this is point-wise, element-wise product. Okay, here, and as I said, is an easy exercise to do. Any textbook you can see, and this is there. Okay, so now this is the part where we are interested in. So by Lotus, what will happen now is. So we were supposed to do gradient phi, right, like this, right? And so gradient phi of this is where we were stuck, right, so far. So with this, this expectation with respect to the q phi, which was originally normal with mean variance sigma, now it can be changed, and here I'm missing this. That's what I was thinking. I'm missing this grad, because grad should not disappear. So so basically, this expectation with respect to q phi now could be written in terms of standard normal PDF. So now it is same thing as saying expectation with respect to standard normal PDF, because the random variable is just now with the epsilon, okay, which is from the standard normal. So basically, this Z that you see here is replaced by t phi x epsilon. Now t phi x epsilon is a random variable with respect to epsilon. Okay, so because mu phi and sigma phi are deterministic vectors, they are constants. So your randomness now falls back on epsilon only. So now if I have to take expectation of this, then I have to know only PDF of epsilon by this Lotus, right? So Lotus was about expectation of g of x, right? And so this you can write this as kind of n PDF of x, right? So what Lotus says is that expectation of function of a random variable could be written as function values for the random variable and PDF of the base random variable. So base random variable is x. So same thing, you can see it here. This is how Lotus is applied on t of epsilon, let's say. Okay. So now expectation t of epsilon, but t of epsilon was actually z, right? So now I'm not really accessing the PDF of Z. So now I'm saying expectation of earlier I was looking at let's say expectation of with respect to Z, right? But then now I'm saying T of epsilon. Now this is rather than looking at expectation with Q phi, and now it boils down to expectation with pi epsilon. So so this is what we get. So then we can do then with Monte Carlo estimation we can have expectation of pi. Okay, so yeah, I mean it went away. So gradient with respect to phi, and gradient we put it inside. Okay, and obviously you have to be a bit careful, because expectation if you see in terms of integral, then it's like saying that when you can interchange integral and gradient, right? So some underlying maths should be there, but we are assuming that this is fine in this case, or it could also be in terms of sum. Gradient of the sum is sum of the gradient, right? This is not in general true, okay, by the way. So you should be a bit careful when you put gradient inside integral. Literally this is what we are doing here. We put the gradient inside. Okay, so gradient phi went inside, and then we have log p theta x t phi x this and right, and this is so basically now with Monte Carlo estimation what we are saying is, since I have to compute the expectation of this guy, I will just approximate it with one of the random samples epsilon. So I will pick some sample epsilon. So it's like in a class I want to estimate the height, average height. So I will pick one random guy and say that that's approximation of the average. But as I said before, here we are saying one, but you could take multiple. Okay, no one stops you from taking k of the epsilon samples, and then you take the average on this, because at the end of the day this is nothing but just average. So in this notation here it's like just take one, right? But we know that just picking one random guy does not give a good estimate of the average. Okay, but yeah, in practice you will actually have multiple of these. So Monte Carlo estimation says that you can get rid of the expectation by just taking couple of samples, and on that sample you do whatever is inside the expectation. So in this case it's grad phi and log p theta. Again I changed this. I wonder if I'm doing a couple of mistakes here, because yeah, I mean this is saying that this this approximates this guy. Okay, so the way I interpret this is a bit not correct. So what we are saying here is that the original quantity that you had here, is very well approximated by this guy. So original quantity you had was with q phi expectation, but now we fall back on pi epsilon expectation. Okay, so this is the meaning of this line here. So basically that's what Monte Carlo estimate does. So overall objective now becomes this. Okay, so overall objective, as you can see here, right, like what I said, actually you will take m samples, not just one like it said here. This is like the extreme case, right? So you will take m samples and take average over the m samples of these quantity, inner quantity, this log p, this like in the loss you don't have this was when we are looking at the gradient of the loss, right? When we are not looking at the gradient of the loss, you just skip this part. So then it's like average of this guy, so which is what we have written here. So for each epsilon you have a corresponding xm. Okay, you are sampling and then you're generating, right? So in this case, like you have sampled m times, you have generated m of them. You have taken an average of that, and you do the same thing for the KL divergence here. You can do this for m of these, but again this this is explicitly kind of can be written down. So overall we have everything in hand. K divergence is an explicit expression. P theta is a neural network, but this could be now also estimated by whatever outcome I get, that I just have to take a log and sum over that. So yeah, so I would like to point out a little bit more on reparameterization trick. So the reparameterization trick, obviously, like we are supposed to, so what it does is basically I'm supposed to do expectation of pz of some f theta z. Then in that case, yeah, if we have to take the gradient, then we take a grad theta of this guy, then the grad theta goes inside, and if it goes inside, and then obviously I end up with this. So in this case there was not a problem. In this case there was not a problem because grad went inside, but the grad was computed with respect to theta, and this theta was not there in the PDF. So that was okay, because then eventually it came out to be expectation of grad theta f theta. Okay, so in this case there is not a problem. But when your distributions are also parametric, then it becomes a problem. So next step we will see what happens when the gradient is being computed for an expectation which is also parameterized by theta, and that is the case we have. Okay, so grad theta, and then their distribution is p theta, and then f theta is there. Now grad goes inside, that's fine, assuming that you can do that. So you can have a look at this if you want to know more on when gradient can go inside the integral. So let us see this. So this is the product rule that we will apply. So the first function differentiation of the second, and then the second and differentiation of the first. Now the second one, the second one seems fine, because I can see this as expectation p theta z, no problem. But here I am in a trouble, because here now I need to know the gradient. I need to do the gradient with respect to theta of p theta z, and this expression cannot be written as expectation now. Okay, there is no way. We don't know whether this could be written as expectation, because in real life we work with samples. We need to compute expectation or average, right? So that's the problem here. That doesn't. So the first term of the last is not guaranteed to be an expectation. And whatever we do at the end of the day, it just boils down to on couple of samples we are estimating things, right? So if there were an analytic solution given to us, then maybe we could have considered that, but this is not true in general. So reparameterization trick, another argument is obviously, I mean, both arguments are kind of coincide itself. So how I compute the expectation and so on, and how the gradient flows in this case. Now this randomness epsilon is now completely separated out. Right? So remember we had, so here I took a figure from outside. So the notation is, and actually the parameter is fine. So this is phi only. So sigma phi. So this is what the encoder produces, right? Mu phi and sigma phi. And with the reparameterization trick, now what we have done is like the epsilon is now separate, and we have sigma phi plus mu phi. So now our samples are like this. Okay. So now I have a clear visibility of if I am going through. So this is the encoder, right? So this up to here, this was the encoder, and from this is the decoder. So up to here, gradient flow was theta, because theta was the parameter of this decoder. So there was not a problem. But here, for phi, I have to pass the gradients like this. Now x has nothing to do with that, because those were your input samples. So you are not going to do gradient flow over there. Epsilon was some taken from standard normal, so that's also has nothing to do with the parameters of a network. So now you have an explicit view that you are going to go for mu and sigma phi. So you will just follow this this way. Okay, so this helps basically. Like there are various arguments saying that if you have this, then it is you are going through kind of a random node. Okay, whereas your random node is now kept separate. Okay, and then you can. So this is a view. Of course, we know that any normal distribution could be written in terms of standard normal distribution anyway. So from practical point of view, this gives a clarity on how gradient flows. Now VAE algorithm and architecture. So let us look into this. One second. So yeah, so let us look into the full architecture now. Essentially, we are done with the variational autoencoder. We will look into the conditional also, but for the okay. So the full scale architecture we have now. Okay. Okay, but where is the? Yeah, it is there. Okay, I thought so. It's like it's shown in two parts. So this is like without reparameterization, and this is with reparameterization. Okay, so here now the idea is simple. You have an input vector x. It goes through the encoder. Encoder is supposed to produce a vector of means and vector of variances. So basically, it will produce a vector, and first half will be mean, and second half will be variance. And then you see them as a normal distribution with mean, mu, and variance. But then you force them to be close to standard normal. Okay. And so that will be forced by KL divergence. KL divergence will make sure that the encoder will produce mean and variance which is close to 0 and 1 respective identity respectively. And then decoder takes samples from the normal distribution, and then it produces FZ, which is the reconstructed image. And then the first term in the loss that I told you, log p theta x given z, that is exactly this reconstruction error. It comes out to be reconstruction error. So that's it. That's VAE, and then this is just a reparameterization trick. So you can see the only difference seems to be just these two. Okay, so in this reparameterization part, we say okay, mean, mu, and variance. You do the sample from standard normal and do a pointwise multiplication with the variance vector, and then you add with the mean vector, and then you let it pass through the decoder and so on. Okay, so that's variational autoencoder. Now VAE results. These were the results. So remember that these were 2013 paper. Okay, this was before GAN. GAN came in 2014. Okay, so these were the handwritten digits. So about 10 years ago, these were the outcomes on handwritten digits. So MNIST, you are all familiar with it now. So GAN and VAE were the two most prominent generative models, and they came within 6 months. These were the dates of archive submissions, 20 December 2013 and GAN on 10th of June 2014. So it's like virtually within 6 months. Okay, now let us look into conditional generation. Just like in GAN, we could generate a conditional image. Now we can do that with VAE as well, obviously. So just to recall, conditional generation is about basically you put some condition. In this case is text to image, right? So so this is what DALI and all this does. But even one can have text to video generation, right? So you may have seen Sora by now. So these are the trends now. So next few years could be text to video, which will become more and more prominent. So you can click on these videos later. Now let us look into conditional VAE, which is really not, which is very simple. Okay, it's just append basically, just like we did it for GAN. So the goal is to generate data condition on additional information. Obviously, it could be discrete class levels, or sometimes you may want to change the angle for the image as well, which could be seen as continuous because angle could be like I want the phase to be 30 degree, 40 degree, things like that. So mathematically there is not much change. Okay, so this corresponds to basically the generator has now class condition. Here the class is y. So given y, now it is supposed to generate x. Previously, yeah, it was generating x and it was taking random samples, but here also it can have some random sample as well to create some variations. So y is the random variable that that corresponds to the additional image or level or view angle, okay, discrete, continuous, and so on. So we can have similar approach that we had before. In this case, we are looking at p theta x given y, and same way we write this using latent variable approach. So now the latent variable is kind of like this. So as you can see in the probabilistic graphical model class, we had, now this is the diagram of this. This is like z, and this is your x. Okay, so this is the graphical model for conditional GAN. Now x depends on x and z is this latent variable. Okay, this is why these are called latent variable models. You introduce some latent variable. So again, our approach could go in a very similar way. We assume that again the generator is some kind of a normal distribution which generates mu vector and sigma variance matrix. So but only thing again you have to notice here is that the generator also is taking that class, okay, that you should not forget. So the generator is also now, generator is not only taking z, it's taking y as well. Okay, so basically if I have to draw the picture, then it is similar to GAN. Both generator and discriminator were taking the classes, okay, because discriminator should also know that this is real with respect to this class, and generator should obviously know that I take a random vector, but this is this condition that I'm given, and discriminator will say corresponding to the condition, okay, it was supposed to be 2 which was supposed to be generated, right? So both generator and discriminator should know, right? So in this case both encoder and decoder should also know what is the class that is being given. So there will be x and there will be y. You can concatenate like that, and then there will be z and there will be y for the decoder, and this is encoder. So this is y, and this is as we know, a generator is parameterized by theta. So we change the notation a little bit, it seems here. So this is our g theta, okay, and it depends on z and y. So z is there for variations, and so you want to generate 2, but you want variations in 2. So that's what the role of z is, right? So z is always there in generative task. Creativity is needed, right? It cannot be just copy paste, right? So that's the role of z, right? So similar to VAE, learning is done by maximizing the variational lower bound. So we can have similar variational lower bound, but it turns out to be very similar. So L phi theta, which is the lower bound of the maximum likelihood estimate that we have, is just that in the maximum likelihood estimate, everywhere instead of x, I write x given y, because it's class condition on y. But everything remains the same, and as we have said that maximum likelihood estimates are really not tractable, and then we go via this variational lower bound route, and in this case again maximizing this L theta phi will make sure that I'm getting closer to the maximum likelihood estimate. Okay, so we do that. Our then focus then goes on into this loss, which is more tractable. Okay, so we do the same thing. We parameterize by neural network and so on. So essentially everything will be the same. Okay, and this approach also we have done it also for the usual variational autoencoder. So these steps are kind of similar. So you replace this by Bayes rule, and this is what we get eventually. So this was the justification, just like we did in the usual VAE. We were trying to justify why variational lower bound is good. So here again we are trying to justify that this is our variational lower bound, which was our loss theta and phi, and this is the actual likelihood. Okay, this is like the gold standard, right? So so we are looking at how our variational lower bound varies from the gold standard. Okay, so and when we look at the difference, we find that this is similar to this. Okay, so basically what this means here is like the distribution that the encoder is trying to produce, and the distribution that the decoder decoder is going to use, they should kind of be so basically working with the various lower bound VLB is same thing as saying that we are minimizing the KL divergence between these two encoder and decoder distribution, which is what we want, right? So by the way, this is like the posterior, right? Posterior distribution. So basically, so the kind of base rule gives us a way to have this consistency, right? So this is something I also talked about in the last class, is something like this. So this is like Q phi encoder, and the decoder is essentially P theta x given Z, right? But not Z given x. So basically decoder is, generator is like this, decoder is like this, and encoder is like this. But if you see in the expressions, it always we see it in the other way, like this. So and this is still like this. So this is like Q Z given x. So this is Q phi Z given x, and but this is the other way. Okay, so this is like this. So this so essentially what this is trying to say is like they should be consistent in this way, right? So the encoder that's trying, so it's like asking it in a different way, right? What could have been the distribution that produced the x, right? So rather than saying given a Z, the likelihood of getting an x, so that probability distribution should be such that if I ask the other way also, it should hold. So what should have been my probability distribution that would have generated Z if I have come via x? Okay, so that kind of match does this consistency thing. Okay, so so essentially if you look into VLB bound becoming closer to the gold standard, it's essentially saying you have this KL divergence matching between the Q phi and the posterior of the distribution of the P generator. Okay, so these are like different views of this. So in the conditional case, obviously we don't want this y to go away, right? Because if y goes away, then obviously your generator becomes degenerate. So that's obvious, right? So because by degenerate, it means that it will start neglecting the class level itself, which is not what you want, right? So what this is trying to say is that we cannot really replace Q phi Z given x y, which is this guy, with the usual one that we had before, which was Q phi Z given x. That obviously we cannot do that, because in that case that would essentially mean that there is no dependence on y, and generator will produce arbitrary image independent of class level. Okay, but that is evident, right? Why should it happen anyway? So in such a case, y is ignored. So there may be cases when you implement, actually this may be the case, the generator becomes degenerate. So that's more of an experimental thing. You have to see why is that, because in GAN also this was some of the issues, right? Because there were mode collapse issues and things like that. So yeah, so one should. Yeah, so that will not be a conditional generator. So that will be the degenerate case. Okay, so conditional VAE algorithm and architecture. So conditional VAE will be very similar. There is no real change, as you can see. The only change you see is the class level. But according to diagram, there is a flip. So class level became the sample, and sample because so I took this from this reference. So you can see that the level is now x, and the sample is y. Okay, so just to mark this in the note. So this is my level. Change of notation. Just to be yeah. So in this case, X is the label and class condition and Y is the sample, and everything remains the same. So what this means, you just append, okay? Technically there is no change in the code. Y concatenate with X, that's it. Condition, that's what you're supposed to do, and the model will figure out that this is taken to be a condition, just like in GAN. And here also decoder, your JET will sample and you will just concatenate this with this, and that should work. And obviously during sampling you will sample JET from normal distribution, and then this is your class, and then it will produce some output based on the class. You have any doubt so far, or so hope should be okay. This is so these are results of the conditional GAN. There were not many results in the paper. I don't know why. They had this denoising result, which I did not find that interesting. This was 2015 paper, so maybe that was still not very prominent time for conditional. So you will see they are sending this noisy image, and they are trying to kind of reconstruct this fully. So if it's conditional GAN, then obviously it is a generative model, so it can create slight variations in the generated image compared to the traditional neural network. And it seems to be better also compared to traditional neural network. If you see here, the 5 is not that good. Neural network could be CNN. We have seen some of the denoising approaches. So yeah, so these were the results. That's all. I did not really find much in their paper. Now, similar to GAN, one can really do a lot of engineering with VAE as well. So unfortunately, I don't have like full set of slides, so I may have to kind of leave early today. But I will get through some of the base ideas of what is going on. So I will go into detail of these things a bit later. I will just give you overview of what one can do with VAE. So just like in GAN, you have seen there were a lot of engineering that went into that, right? So there were like progressive GAN, and there were like style GAN, and specifically when we look at style GAN, then it was about latent space engineering. So basically, you wanted to have a hold on the features, okay, a fine-grained feature engineering basically, and you could do this via generating some nice W vectors, and then you could inject that at multiple places, right? So this was the latent, and then there were many fully connected, and then you were generating the W vectors, and then you have some constant block here, and then you have some con block with some adaptive normalization schemes and so on, and then you had the generated image X. And then in the style GAN, so basically this W vector, if it was injected somewhere here, then it will have certain effect on the features. If it was here, then it will have certain effect on the features. And then there were some additional noise vector here, which could also be added with some amount of concatenations, and that can also affect the features. You can control the features. So when you are building an app, you will essentially do this thing. Obviously, offline, you will kind of figure out which does what. So if this is responsible, let's say for hair color, then you will encode that in your app, and then there will be buttons in the graphic interface where user can just click on that, and then by changing the noise vector here and the fact that certain latent space are responsible for hair color, then the user can kind of change color and things like that. So as we have seen, there are many ways to control this. The only difficulty is it is not very clean, in the sense that it's very like you do this random stuff and see which effects you see. Okay, and as such, it's a hard problem basically. How will you know anyway, right? So these are like latest space engineering, and if we come back to so in GAN, the problem with GAN was you did not see the the encoder distribution explicitly. In fact, in VAE, the generator itself is a distribution. So you have explicit knowledge of the distribution itself from where you are sampling. So VAE is an explicit model. It gives you explicit distributions that you will sample. Obviously, it's a complicated one because it's a neural network parameterized. In VAE, you may have a little bit of flexibility. So this flexibility is something that could be exploited up to very latest results, like what is that? Video GPT. Yeah, Video GPT. That's like one of the recent results a couple of months ago. Okay, so we want to see what could be done here. Okay, so let us see. So in VAE, what they do is we have encoder in VAE, and we have some input samples. So these samples are like that, and it goes through CNN encoder. And of course, this encoder, the way we learned so far, is that encoder basically is some distribution, okay, with some vector of means and some vector of variances. Okay, so this is our encoder that learns a normal distribution, and this normal distribution, we know normal distribution is a continuous distribution, right? Now, as such, from a continuous distribution, I have infinite possibilities to sample. Infinite ways to sample, right? And the question is, do we really need such a large variation in sampling? Like, if I have to interpolate between a cat and some flower, like is there a really very continuous way to interpolate, or if there are like similar dog image here? Okay, so I'm not confident about drawing dog. So let us say this is dog 1 and dog 2. So should I really look into a continuous interpolation between these, right? Or when we remember various objects, is it necessary that we do continuous interpolations in our head? Okay, I mean, these are philosophical questions. Of course, we don't know clearly how our head works as well. So in VQ VAE, it's called vector quantized VAE. Full detail we will come to that. I just like could not prepare a full slide somehow, so I'm not feeling well. So here, if you see, rather than having this continuous distribution, which is normal distribution, what they suggest is that you build a dictionary like this. Okay, and in this dictionary you have k items. Items are like embedding vectors. Okay, so obviously k is finite, right? K is finite, so the goal is to go from continuous samples to one of these embedding vectors. Okay, and the question is, why should it help? Right? Why going to these k of these embedding vectors is useful? Okay, so we will see that one of the immediate use is video generation. So let us see on a course level what this is doing is that it produces a let's say initially it produces some random vector Z. Okay, but then this random vector Z is now compared to one of these embedding vectors, let's say some nearest neighbor search, okay, and then it is mapped to one of these embedding vector. Let us say we produce some Z1 and it is mapped with E3, okay, some you can do some nearest neighbor search and so on, okay. So I mean you can visualize it that way, but we can make it learnable, okay. What are these embedding vectors also we can learn. So initially Z1 may go, and Z1 there is initially maybe these are like kind of like random. So you can see these embedding vectors also as weights, parameters of your model. So parameters are now parameters from here, decoder, or like the encoder, decoder parameters, and these embedding vector parameters. So you have now 3 parameters, okay. So let us say phi, theta, and xi. So this also you can learn in the process, okay. So we will build a loss function maybe in the next class, but right. So what will happen is that you will create a Z1 through encoder, and then this Z1 will be mapped to one of these initial randomized one. So it will go to some EK, okay. And similarly Z2, Z3 and all those will be mapped somewhere. If they exceed K, then obviously they will try to go to the closest one and get matched there. So assuming that you have learned this nice embedding, which are kind of discrete because there are only K of them. So what you're trying to do now is that you are saying that I have seen so many variety of images, variety of dogs, variety of so dog images embedding, we are expecting that they will be nearby and they will be matched to one of the EI only, okay. So so this way you are kind of having a more discrete or quantization of these vectors. So once you have that, then this is what is then passed next to the decoder, okay. But only these EIs get passed to the decoder, okay. So so these EIs only are now going to the decoder, and obviously here we are saying like we had like many of the EIs produced. It's like many of the ZIs produced as a batch, and many of the EIs produced as a batch. And then this will be taken by the decoder, and then it will produce based on these embedding. It will produce some relevant images. So this is what they call it, a code book, where so we will write down the details of the loss functions in the next class. Okay, so what can we do with this, right? We can do many things with this. So now let us see. Our VA model. So VA model has encoder and it has decoder. Now what we have done is that we have made the latent space kind of discrete. So we have like K of these latent space. Now imagine a video of length, let's say 1 minute, will have like per second we have like 30 frame or something like that. So you can make them into kind of slices. So these are your video slices, right? So you video, you see them as frames, right? As a time sequence. So you stack them as a tensor, let's say, and it passes through the encoder, and each of the frames I could map it to some discrete latent here. Okay, so then each of these discrete latents are kind of so then they look more of a so what I'm trying to say is that rather than looking at this as a discrete set of embeddings, not like following any ordering, now in the video case I will see them as ordered discrete latents. Okay, so then in that case I know that there will be ordering. So then the decoder will be some some network like RNN or transformer that is autoregressive in nature. Okay, we will look into these things in detail in next class. So the idea here is that this set of extracted latents that you have, if I can have a ordering as well, okay, the first frame encoded as E1, second frame encoded as E2, and so on, then these are like sequence E1, E2, E3, EK, and so on. And this now goes into RNN. Obviously, we know RNN processes like this. It goes into E1, and then next step it goes into E2, and so on and so on, right? So we will train a RNN that it takes a time series data, in this case is video, and it learns to produce the video sequence. Okay, so that is useful in this case. The fact that we could discretize this latent, we could produce a sequence. Now philosophically also, if you see, this has been a big problem in video generation, because in video generation there is a time thing, and as such the space is used. So the problem, a challenging problem in video generation is what is to be really memorized and how efficiently it should be memorized. Okay, well, how to maintain this coherence nature and so on. So this representations where we have the key ideas captured in a sequence, in a time sequence, and knowing how to reproduce them, that is critical. Okay, so this discrete latents somehow are still manageable. We are expecting that they are smaller in size compared to the original image, which could be very big. What we are really telling to the decoder is there are key moments which are enough to learn. So any video generation task follows some sequences, and what are the critical things that one should learn while generating, right? So there's like one level of more difficulty in video generation, and this seems to help. The code book now is maintained in a sequence now, and there is a although we don't know the details of Sora, OpenAI video generation, but it seems the overall plan, the way that they said in the paper, it seems like they're doing very similar to this. The ideas that they're using is very similar to what we are looking at now. Okay, because as such it's a very hard problem. So you are supposed to maintain this underlying change in a compact way. Yeah. So basically now for decoder you can use anything as you want, as I said, RNN, CNN, whatever. So there is a I don't know if this works. So these guys are really planning in this way only. Okay, so they want to do this VQVAE. So if you see this, they call it Open Sora plan. So Open Sora, yeah. So Open Sora, but we prefer to call it closed. Yeah, this is like a bit political, but you see their idea is similar. In fact, this is what was bit revealed by the Sora paper. If you can see, of course they don't tell you the details, but they were saying something like this. It is mapped to some discrete latents, and then we try to kind of use some transformer models to regenerate that, and so on. So this is their, yeah. So this is their plan, and this is more or less their plan. So they call this space-time patches. Okay, and then it goes into these diffusion transformers, which is a sequence models. So the arrow goes like this, I guess. Yeah. So this is encoder, space-time patches, which is actually VQVAE. In fact, they say this later. And then a sequence of these latents. Now you use them. So this sequence of latent, you may, yeah. We don't know exactly what exactly they may be capturing, but and they seem to have some condition as well. So I'm not sure completely about what these things are. So they have this video generated, which doesn't look that bad. It looks quite smooth. So this is quite active. You see 10 March and so on, and this is these are their plan. So video VQ GAN is also they have, and actually if I have to say about VQ GAN is just a top up of what we saw. So if you see VQ GAN, VQ GAN is just saying that that whatever the decoder is producing, you add a discriminator on top of that. Okay, so that's all you have to. So there is something called VQ GAN also, right? So we have, so someone came up with this. So what we saw is VQ VAE, and then later someone did VQ GAN. Now VQ GAN, what it says is that, okay, decoder is producing something, but let me pass it through discriminator as one more step. Okay, so then the discriminator is seen as one more way to like just the quality of the image that was generated. We can look into detail of this, obviously. So that's not a big change. We can look at that a bit later. So that's what they seem to be using. Yeah, so they will be using clip embeddings and all this, obviously. So, and these are some of the image videos. They're still not that good with Sora, but I think it will catch up. Yeah, this is open source. Yeah. Okay, so I guess that was today's class. So we essentially stop at video GPT. There was one paper on, yeah, this paper basically. So video GPT we will look at. Open Sora is ongoing, so we don't have to really. So video GPT we will look at what are the more details about this. We will see that later. And VQVA obviously we will look at. VQVA is used in video GPT. So okay, so let us stop for today. Thank you.